Hey there everybody, Mr. Dickin here, and in this video we're going to be talking about applications using derivatives. So when we do things with derivatives, typically what's going to happen is we're going to have some sort of a function, and if we use derivatives, we can figure out kind of what is happening with the slope at certain values of x. Another thing we can determine is specifically when our slope of a tangent line is 0. So we're going to try to figure out when is our derivative equal to 0, and that's going to pinpoint either a minimum or maximum value. So let's first take a look at a problem here. We have an arrow being shot into the air. They give us the height function, where t is time and height is in feet. It tells us to use a graphing calculator to type this in. So we type this in into y1, and then get a logical window setting so that way we can see everything. And here you have where we'd enter into our window settings a good x min, x max, and y min, y max in order to see the whole function. Now I'm noticing this is a t squared, so it's going to give me a quadratic function, and it's got a negative coefficient in front of it. So graphically speaking, I'm anticipating that we're going to see something that looks like this. Furthermore, I'm noticing that we have a 5 as the constant. So when time is 0, the height would be 5, aka the y-intercept would be 5. So at the point 0, 5, when time is 0, our height is 5. All right, let's see what they're going to ask us here. What is the maximum height the arrow will reach? Well, the maximum occurs right at the top of the parabola. So what we could do is, using our calculator, we could figure out the left bound and right bound if we're doing our calculations to find a max. Or what we could do is figure out when is the derivative equal to 0. So if we're using our derivative and setting that equal to 0, I'd find the derivative function h prime of t, and that would be negative 32t plus 72. Well, if I were to solve that out and set that equal to 0, we would get a t value, and you can kind of see it underneath here, of 2.25. So if I were to solve this out, let's move that 32t to the other side. I'd get 32t equals 72. Divide both sides by 32, and we'd get our answer. Now, when we get our t value of 2.25, we could plug that in for t to figure out the height. If you were to do this on your calculator and calculate the maximum, it will give you both the x and y values in one shot. Part D says, on your graph, what is the slope of the line tangent to the maximum? Well, we already kind of discussed that, right? Anytime we have a max or a min, the slope at that moment would be 0, would be a constant. All right, let's go on. How high off the ground was the arrow when it was first shot? This is asking for the starting height. Well, that's just your y-intercept. And that is just whatever the constant value is from the original function. So that function we saw had a bunch of stuff. We had a t squared, we had a t, and then there's a plus 5 at the end. That plus 5, that is our y-intercept. Next, at what time will the arrow hit the ground? Well, we have two options here. One is we could use our calculator. Again, we know the shape of this thing. We could figure out what is the x value for this point right here. So we could go to our calculations menu, select 0, and then establish a left boundary and a right boundary. That's one method. Or, if we know the function, we could always rely on good old quadratic formula to solve that for 0. Now, when we're doing this and we're figuring out when does it hit the ground, there's technically two spots, right? There's technically this other x-intercept over here, but if I think of this as being a relationship between time and height with respect of time, I really don't care about anything that happens back here because that would be negative time. So I really don't care about anything going on back in this section of the graph. Number 2, a ball was thrown upward into the air. The height can be given using the following equation. Well, this is just like what we've seen before. I've got a function. It's a t squared, negative, so it opens down. Y-intercept is 6. So if I'm visualizing a graph, here we go, shabam. That y-intercept, again, would be 0, 6. It says, when does it reach the maximum height? Well, here's the maximum. I want to know what time value is associated with that. And then how high was that maximum value? What height is associated with that? So if I get the maximum value right here, if I can figure out what is that point, x comma y, although we're not using x's and y's, we're using t and h of t, that would give me both answers. Well, if I have my graphing calculator, I can just punch that in for y1, and then I can use my calculations options to figure out the maximum. Or I could find h prime of t, which would be negative 32 t plus 80. If I use what I know about the maximum having a tangent slope of 0, I could set my derivative equal to 0 and figure out at what t value is the slope of my tangent line 0. At what t value is my slope a constant value? When we solve that out, we'd get a t value of 2.5 seconds. Once you have 2.5 seconds, you can go back to your original function. If we want to know how high it went, well, let's just plug in 2.5 for t and see what we get out. From what height was it released, aka starting value, aka y-intercept. We already knew that. That was going to be 6 feet. Then find h of 3. Well, h of 3 is saying if my time value is 3, what is the height? So if I go to my original function and plug in 3 for t, I'd have negative 16 times 3 squared plus 80 times 3 plus 6. If I were to evaluate this function out, that's going to tell me after 3 seconds how high is the ball. If we do that, we should get 102, and this should actually be feet. Okay. Is the slope of the tangent line positive or negative at 3? Ooh, slope of the tangent line, aka the derivative. Is the derivative positive or negative? Well, we already calculated the derivative. Where did we calculate it? I know it's over here somewhere. There it is. So the derivative function is negative 32t plus 80. And I want to know when t is 3, what is the value of that thing? So let's figure this out. Negative 32t plus 80. And we're plugging in 3 for t. Well, this would be negative 96 plus 80. That would be negative 16. So the slope is negative. Well, if the slope of the tangent line for a position graph is negative, that means the ball is falling at 16 feet per second. Because it's negative, I know it's falling. Part F, is the ball on its way up or is it on its way down at h of 3? Well, it's on its way down, right? It's got a negative slope, so it's heading downward. Visually, if I were to kind of imagine this graph, a t value of 3 would be somewhere past the maximum, so it's coming back down. It says, name a time t in which the ball is on its way down. Is the slope of the tangent line positive or negative at this time? Well, we could really name any time value past that maximum, and we already know the maximum occurred at 2.5 seconds. So anything beyond that 2.5 second mark is going to have a negative slope and the ball is falling downward. So here we just use t equals 4. You could do 2.6 seconds, 2.7 seconds, 3.1 seconds. Any time after that maximum value, our slope is going to be going downward because our ball is falling. All right, now let's get into something called projectile motion. First, some definitions. Displacement, the change in distance between the final and initial positions of an object. So you're going to do the final position minus the starting position, later minus earlier. So if I want to find the displacement of an object over the interval from 0 to 4, based on this function, I'd need to plug in 0 for x, which we're doing here. I'd need to plug in 4 for x, which we do over here. So when x was 0, our y value is 0, and when f was 4, our y value is 8. That means over the span of those 4 units, our y value changed by 8 units. When we get into this, we're going to start seeing graphical representations, and these are the two values we just found. So we want to know how far did this thing change in its y value over that span. Next, average velocity. Well, velocity is just distance compared to time. So the average velocity is going to be the distance traveled over the time traveled. Essentially, it's going to be the slope between 2 points of a position graph. Now, we say average rate of change because we're assuming to go from point A to point B here, we're just going in a straight line. That might not be the case. I might have taken a whole bunch of wonky, wacky turns to get there, at which point, I might be going faster, slower, forwards, or backwards. But if I traveled 8 units over the span of 4 seconds, we could get a velocity, which would be 2. Sorry, average velocity, I should have said. Now, instantaneous velocity talks about one specific point in time. So if we're looking for instantaneous velocity, that should be a trigger in our brains that we need to use the derivative. Okay, because that will tell us the slope at any given point. And I can't spell slope. Now, if we have a positive slope, our velocity is going forward. We have positive velocity. If we have a negative slope, our velocity is negative, so we're moving backwards. All right. If we're talking horizontal movement, forwards is going to the right, backwards is left. If we're vertical movement, positive velocity goes up, negative goes down. So if I want the instantaneous rate of change at x equals 1, first I need to find the derivative of x, so f prime, which would be 2x to the first minus 2. And then if I plug 1 in there, I get 0. So that tells me the derivative when x is 1 equals 0. That means I have either a min or a max at 1, because the slope of the instantaneous change right there, or the tangent line, is 0. Number 3, a particle moves on a line away from its initial position, so that after t hours, it is s equals 3t squared plus t miles from its original position. Find the displacement of the particle over the interval 1 to 3. So we need to figure out, where is this particle at 1 hour? Where is it after 3 hours? So right here, we're finding basically s of 1 and s of 3. So after 1 hour, it was 4 miles away. After 3 hours, 30 miles away. The change between 30 and 4 is 26 miles. Part B is saying find the average velocity over that interval. Well, we know how far we were displaced. And if it was from 1 to 3 hours, that means we waited 2 hours to get that displacement. So to calculate average velocity, it's just displacement over time. If we want instantaneous velocity, we first need to establish the derivative function. So the original function was 3t squared plus 1t, which means our derivative would be 6t plus 1. Once I have my derivative function, I can plug in a time value of 1 to get a specific velocity at that moment. All right, number 4. Let y equals 2x minus 1. Find the average rate at which y changes. Average rate at which y changes. Average rate of change. Change in y over change in x. Over the interval 1 to 4. So what we need to figure out is, what is f of 1? What is f of 4? This is nothing more than just basic slope formula. So we're going to plug in 1 and 4 into our function, see what we get. We get 1 and 31 respectively. Change in y values, 31 minus 1 is 30, over change in x values, 4 minus 1 is 3. We would get an average rate of change of 10. Find the instantaneous. Remember that word instantaneous means we have to use the derivative. So we find the derivative function, y prime is 4x, and for a time value of 1, 1 gets plugged in for x, we would get 4. All right, number 5. During the first 40 seconds of rocket flight, the rocket is propelled straight up so that in t seconds it reaches a height of s equals 5t to the third feet. What is the average velocity of the rocket during the first 40 seconds? Okay, well, average velocity, that means if I were to visualize a graph, right, we're going to have a rocket. The rocket launches up, comes back down. So I want to know starting height to the height at 40 seconds, what was the average velocity? How far did it travel? How long did it take to get there? Now, this isn't going to be a perfectly straight line in regards to the actual function itself. So we're just finding kind of an approximation here with the average velocity between those 2 points. So we are finding the height at 0 time, the height at 40 seconds. Those are going to tell us our function values, change in function values over the change in y's. Down below it's technically 40 minus 0, but that's just 40. Next, what is the average velocity of the rocket during the first 135, this should be seconds of its flight? Well, we're going to figure out, or maybe it should have been feet. No, my mistake, people. Should have been feet. So they tell us a height value, and we have to figure out time-wise how long did it take to get there, which would have been 3. So the change in height was 135 minus our starting value of 0. Change in time was the first 3 seconds. So we can calculate the change in position over change in time to get your velocity. What is the instantaneous velocity? Well, again, instantaneous, find the derivative. So the derivative of the function 5t cubed is 15t squared. And if we want to know what is the instantaneous at the end of that 40-second interval, so I want to know on that 40th second, how fast is this traveling? Well, I just plug in 40 for the derivative, and we'd get 24,000 feet per second. All right, number 6. A particle moves along a number line so that its position is given by the function t squared minus 6t plus 8. S is meters, t is seconds. Find the displacement. So displacement is change in y values during the first 4 seconds. Well, starting value, we're at 8. After 4 seconds, we're at 0. So this thing went from 8 to 0 after 4 seconds. It decreased by 8. It went backwards. So our displacement is negative 8 meters. All right, we'll do part B here, and then number 7 we're going to carry on with the next video because I don't want this one to go too terribly long. Find the average velocity during the first 4 seconds. Well, we know the displacement was negative 8. We know the time, so we have the change in position over the change in time. We can get negative 2 meters per second. The instantaneous velocity, well, we're finding the derivative then, which would be 2t minus 6. When t is 3, we plug 3 in for that. So it looks like s prime of t would be 0, meaning our instantaneous velocity is 0 at that moment, which tells me we have a maximum or a minimum occurring at 3. So this value is probably going to be 3 on the x-axis there. At what values of 3 does the particle change direction? Well, if it's switched from positive to negative or negative to positive slope, that means it has to go through 0. So anytime we have a tangential slope of 0, that's when our function is changing from going downhill to uphill, going negative slope to positive slope or vice versa. So anytime we have a slope of 0, that is a change point from positive to negative slopes, or a change in direction. Part E, where is the particle when s is a minimum? Well, we already know that occurs at 3 for t, so let's just plug in 3. So if I plug in 3 for t, I would get negative 1 meter. So this point over here on the graph would be at 3 comma negative 1, and that is my minimum. All right, we will postpone number 7 and onward for the next video, but you know the drill, folks. If you have any questions, do not hesitate to reach out and ask. And as always, good luck, have fun, be safe, roll tide.